Hello, Calc 2 students. We are about to do 4.8/8.2. We're going to go back to 8.2, but first we're going to talk about parametric coordinates. It's our second to last lesson for our e-learning that we're doing in 2020. So I'm going to do this with Desmos rather than a DocCam because we are going to do quite a bit of graphing, and I'm going to show you how to do this stuff in Desmos. So parametric is a little different. If you look at your workbook, I'm hoping that you'll have your workbook out with you while you watch this. So if you go to page 60, it asks you to graph a bunch of things in parametric, and the way you do that, I have this notation on the workbook that looks like x of t, y of t. The way you do that is you pretend it's a point in Desmos. So you can see here, I made the x value cosine t and the y value sine of t. So this is called parametric because there's a third parameter, t, is time, and you can look at how this looks like part of the unit circle. And if I let time go to 2 pi, this is the whole unit circle, and it's going this way. One way to tell that it's going like this is to change this number, and then you can see as it goes around what's happening. That's a little clunky, but if you make a slider, we want the slider to go maybe from 0 to 2 pi. Sorry, things are getting crazy here. 2 pi here, and it's a small step, and then you can watch it get traced out. And that also makes sense because that's how the unit circle works, right? Cosine is the x value, sine is the y value. So you can use sliders to help you kind of see what's going on with these. So basically this part says, here's some examples. We're going to graph these. The next 3 examples are all the same thing, but slightly different. So we're going to keep the b there for a parameter, and these all say go from minus 10 to 10. So we'll put minus 10 here, and we'll make b go from minus 10 to 10. And we'll have a step of 0.5 maybe. And the graph we're going to do, the first one says t for x and then t squared. And now if you think about if x equals t and y equals t squared, y equals x squared, right? This should look like a parabola. Of course, right now you don't see anything, but now you see this parabola. This one's going left to right, so you don't see this because it's way up here if I'm doing this right. Yep. And it goes from minus 100 to 100 because I'm only going from minus 10 to 10. You square those values, you get 100. Okay, so there's a parabola. I'm going to do the same thing. Is there a way I can duplicate this? I'm going to do the same thing for 3. I'm going to use e to the t, however. And then e to the t quantity squared. And so we're going to use the same slide. We're going to go from minus 10 to b. B here. Okay, and we'll see what happens with this graph. We'll close that one. Okay, it took a minute to show up, and now you see this still looks like y equals x squared. You can see it's the same graph. But things are a little bit different. The green one doesn't show up at first, and then it goes faster. You can see there the red one behind it kind of isn't going as fast. It'll catch up, but the green one will go much farther. You can see that green one shooting off to the right. Okay, why is this? There's a couple things that are different. The first thing, the reason the graph goes farther is because e to the t, 10, rather than 10, that's 22,000, right? So this graph goes way farther because the last x value put in really is that number, not 10. The other weird part is that it doesn't show up on the right side. So when you think about b being really small, right here, you can see that little blob of green right there. Well, what you're really plugging in at this point is e to the negative something, right? So if you think about e to the negative 6, that's not negative. That's a very, very small positive number. So in this region, you're not putting in negative numbers, so you're not getting the left region, the left quadrant. You're getting really small positive numbers. So you get this little kind of dot here. And then as you grow, then you get the big numbers and it shows up. So it's still y equals x squared, but it's a whole different part of it at a different speed. And that's one of the key points of parametric graphs. Okay, so let's compare, not this one, but let's do the next one, which is sine t. And then we want to square sine of t. Same idea, minus 10 to b. And start with nothing here, except for this little dot. Well, that looks like x squared, but then it comes back. And you'll have to look real close to see this getting darker. But as this plays, the green stuff gets darker and darker. That's because I'm going back and forth like a pendulum. So it never goes past -1 and 1 because sine can't be bigger than that, right? So I'm never inputting x values more than -1 or 1 because it's really this thing is the x value. So it never gets past that. And then sine is periodic. So the numbers I'm putting in are sine values that go back and forth, back and forth. And so this actually swings around like a pendulum. I think another way to do this is just to put b here. And that creates a dot, and you can see the little pendulum spot go back and forth like this. So that's where it's at any given time. That's another. So these are some good tricks to use when you're trying to figure out parametric graphs. That's why I'm showing you this on Desmos instead. So those three graphs, sine with e to the t, and then just regular t, those are all the same graphs, sort of, but they're doing different things because of the way we wrote them. Okay, this last graph we're going to do some calculus on. And so we're going to talk a little bit about functions here. This graph is, again, we're going from -10 to 10. It's t squared. Then it's going to be t cubed minus t. And this is a graph that you would say is y is not a function of x, and that's true. However, x and y are both functions of time. So this actually makes sense. We'll do our little dot again. And at each point, or each time, there is a point that makes sense here. So let me do this here. Okay, so I've got my little dot, and let's see. You can see him. As the graph appears, you can see the dot kind of leading the charge here, right? So you think this point here would be an issue because you shouldn't have a derivative there. You're crossing your own graph. It doesn't make sense, but you're crossing the graph at two different times, right? There's this time, and then there's this second time. So in parametric mode, that makes sense. It's kind of like if you're driving a car and you cross where you were before, but at a different time. Okay, so what we want to do next is we want to take derivatives. And the reason why we're doing parametric now at all is because we're headed to doing parametric arc length. And we were just doing arc length on rectangular graphs. Now we're going to show you how to do it with parametric graphs. And so to do that, we're going to take a derivative first. So let's look at this function, and I'm going to just type up here what the formula is. This is on your notes. It's dy dx is dy dt over dx dt. And this isn't really good math, but you can kind of think about the dt's canceling, so that makes sense. But that means take the derivative of y with respect to time and x with respect to time, and you'll get the slope, the dy dx slope, but it's going to be a function of time. So let's do that. So dy dt is going to be 3t squared minus 1, and I'm taking the derivative up here of this y coordinate. And then dx dt, since I'm typing stuff Desmos doesn't like here, we'll do it all in the same line, would be 2t. And then the actual final derivative, dy dx, I'll put it up here, would be 3t squared minus 1 over 2t. So I could graph that, but it doesn't make a lot of sense because this is slope against time, and what my picture is x against y. So graphing it really wouldn't be that interesting, but I still want to think about it. The next part on your page 60 in your workbook asks about where's the derivative undefined, and does that make sense for the graph? Well, it would be undefined when time is 0. That's the denominator. So let's go to where time is 0. Okay, that spot here. If you go just a little bit past that, I want B to be a slider still. So, sorry about that, guys. I want B to slide here, but if you make B 0, and you go right there, you can see that you get a vertical tangent line right there. So that makes sense that the derivative is not defined. The other place that is of interest is at the top. When is the derivative 0? Well, that would be this flat part here and then the flat part down here. If you set the top equal to 0, I think you'll get square root of a third. Let's do that for B. And you can see that's where I'm about to make the 0 slope and then negative square root of a third. And you can see that would be the other spot where you're about to get a 0 slope. Okay, so taking a derivative is just take the derivative of the two parts and then divide them. But then that slope tells you, that function tells you the time at which the slope is what you want it to be. Okay, so let's get rid of b here for a minute, and then add the slider back. Okay, so I've got this curve, I'm looking at this. I would also like to figure out, if I zoom out, this whole crazy thing with the bow, all the way from -10 to 10, it gets pretty far out, I think it goes to 1,000-ish, yeah. So this whole thing, I would like to figure out its arc length. It's a pretty big curve, we're going to get a big number. So our arc length before was this formula. You had a and b, and you had square root 1 plus dy over dx, which was the derivative, or we had f prime of x squared dx. So before we got to that point, we factored out dx, but really it kind of looked like this first, dx squared. If you think about that outside being a dx squared and pushing it back through, it's really this, except you need a differential on the outside. Well, if you think about multiplying that, dt through there, or pulling out a dt squared, inside it would look like that, and then when you square it on the outside, it looks like this. So think of the outside one as square root of dt squared, and these are actually all the same expression. That means for parametric, this last thing, well, you really need a time, so we'll call it maybe t sub a, or t sub 1, and a second time. But you're just going to take those two derivatives that we just used for dy dx, the x derivative of time and the y derivative of time, and those are going to be your two squares. So let's go ahead and use that formula then. This curve would be -10 to 10. Those are the times. And we just did these derivatives. It was 2t squared plus 3t squared minus 1 squared. Okay, and you get almost 2,000. And that should make sense because I'm checking the length of this, and it doesn't quite go up to 1,000. If this was straight, right, it would be 2,000, and then it doesn't. It seems like it should be longer because of this part. But if you zoom in, it doesn't go all the way to 1,000. So if you played this straight and made it go farther out, 2,000 seems like or 1994 seems like a reasonable number. It's not a crazy term for this curve. All right, so that's how you do parametric arc length. And then on the next page, there is a thing about parametric motion, about graphing based on other parametric graphs. We are going to skip that. I'm going to do something a little different. A lot of your problems on your WebAssign are about lines and circles. So let me just show you, back up a step, and not arc length, but just show you how to do lines and circles in parametric. So you already saw that cosine t, sine t gave you a circle, or the beginning of a circle, and then if you want to go farther, 2 pi. If you want to change the radius, you're just going to put a 5 or 3 or whatever the radius is. That's an ellipse, but if you put it on both, you get a circle, and whatever number you put out here is the radius. That's actually kind of nice. And if you want to shift the center, well, if you want to shift by x, plus 2, look, I moved the center over by 2, so that's 2, 0 is the center. And if I add to the y value, the center is now here. Oh, sorry guys. 2, 1. So it's actually pretty simple. If you can remember cosine and sine, multiply on the outside to change the radius, and add to change the center, or subtract if you're going to go down. So that would make the center go to -2, 1. You can also do other things like change the speed and the direction. So the way I'm going to do that, let's get rid of all the center stuff and the radii. Those rules will stay the same. But let's go ahead and make a point here, cosine b, sine b, and you can see this guy tracing around the way he should. What if I did it backwards, sine t, cosine t? Well, that makes the same circle, but if I go up here and I go sine b, cosine b, this is going to be traced in a different direction. So right when you start at 0, which is where I'm close to, we'll just say it's close enough, I'm at the top, and then I'm tracing clockwise instead of counterclockwise. So I started in a different spot, and I trace a different direction. You don't really need to memorize which way is which. You can use technology to help you out here. Another thing is if you made one of these negatives, maybe start with cosine t, but then you go negative sine t. That's a little crazy. What would happen here? So cosine B, it's still the same circle, negative sine B. Now you're gonna, let's see, let's go back to 0. You're starting where you normally would start, but you're going in the opposite direction. So there's lots of different ways to change the direction and where you would start. And so some of those questions will ask you about that. No matter which way you do cosine and sine, the radius and the changing the center will be the same. One other thing you might try is changing the speed. So if I just put 2b here and 2b here, I want these to be the same. This will make it go twice as fast. So it'll take fewer angles. And if you compare that, if I compare that to cosine B, sine B, you'll see what I'm talking about. So the purple dot should be faster than the blue dot. And you can see it's going faster, right? It went around twice while the blue one went around once. Okay, so those are circles. Another thing you could do are lines. And so what you're going to do if you want like y equals 5/4 x plus 2, with the x on top here, I'm going to split the slope into the rise and the run. So I'm going to pick a point, and let's pick an easy point, so 0, 2. So x is 0, and y is 2, and we'll add some stuff here. The rise is the first part, so that's the 5, so 5t. And the amount it goes up 5, it should go over 4. And you can see this is that graph. So the 0, 2 are just, I picked a point, that was the easy point to find. And then 5t is saying in 1 unit of time I should go up 5 units and I should go over 4 units. So that's why the 4t is with x. So I'm just breaking slope apart into 2 pieces. I didn't have to pick 0, 2. I could have picked, what's another point on this line? 4, 7. So I pick 4 plus 4t, 7 plus 5t. That's the same graph, just farther out. And of course, if I change time and make it bigger, I get bigger chunks of the line. And I could use the... I could subtract or add. If I subtracted both the slopes, it would just go in the other direction. So if you look at this, right now this should go up from right to left. If I subtract these both, you see it went down. So as I go out here, I should get more to the right. So, or sorry, to the bottom left, because I'm going down this way. So that just reverses the flow of the graph, but it's still the line. So you can tinker with these, but in general, splitting the slope here and then having a point to start. So let me do one more of these. So you can maybe pause me and try it yourself. If I wanted to do 2x plus 3, so I need to pick a point to start. 0, 3 is probably the easiest point on the graph. So make x 0. And my slope is 2, so as I go up 2, I should go over 1 in x. Y starts at 3, go 2 in y. And then there's that. And like I did for circles, you can speed this up. If I take both of these times 5, say I go 5t, 10t. Well, 10 over 5 is still 2, so it's the same slope, but in 1 unit it goes 5 times as far. So that's why it's way faster up here in the same amount of time. Okay, so those are lines and circles, and that's everything you should need for parametric. And then there's a Plicker's problem at the end that we're going to skip, but that should be enough to get you on your homework. If you have questions, let me know.